Was anyone on simple Binius yet? No. Okay.
No, I've already read the post.
You already read it.
Yeah.
Wait. So then, okay. In the
I'm
first.
checking the code now because I didn't like really get into the code.
So maybe my question is, in this simple Binius section, these 16 numbers. What are these numbers?
So for now, you just need to understand how you can flatten the cube.
Yeah, but like that flattening, this like 1, 1, 3, 4. Like, what are all these numbers?
Yeah, but for now, it's just like to understand the data structure. But then,
Oh, I see.
what you're going to commit inside this cube is like.
Oh, I see. I see. These are just regular integers as our field for convenience.
Yeah.
I see. Binary field elements. Okay, I see. I see. Well, I'm confused. It says in the simple Binius, it says the prover should not be able to know or be able to guess S. That's supposed to say R. After they make the Merkle tree.
Let me check. Where is that?
So the first time he shows a picture of a Merkle tree with a root, he's like, now let's suppose the prover wants to prove blah blah blah. And then on the third line it says prover should not be able to guess S until after they committed to the Merkle root. That should say R, right? Yeah, I think that's correct.
I'm wondering if he's like the S is referring like to the secret in the polynomial commitment scheme.
What is the secret? Well, it makes sense if it's R, right? So what is the point of this like linear combination of existing rows? Did anybody at this point in the post yet?
I'm just reading that part.
Yeah.
Yeah, and I have the same question.
Okay.
So I wonder what's the purpose of this polynomial 1 minus alpha as a tensor product of.
Yeah, I also don't understand the point of this tensor product. Okay. Also, how is he getting 3141 times 6 equals 41? Like, where is this coming from? Or like that partial evaluation, like, what is he actually doing there?
So do you mean this part?
Like, so I mean,
This one?
like, yeah, exactly. The first line here. So here he calculates 3141 times 6 equals 41, right? And then for each value, like what is this multiplication he's even doing here? Oh, it's 3 times 6 plus 5 times negative 9 plus 5 times negative 8 plus 12 times 9. Okay, got it. Never mind. Yeah, I got it. So where's negative 137 coming from? Anybody get that?
No, I don't get it either. I'm checking the Python code that he
Yeah. The problem is the Python code is evaluating it at a specific point. But here that's not the input to the function, right? The input to the function here is 1, 2, 3, 4. But the code that he pointed to is like has 1, 2, 3, 4 and then the numbers that he's actually evaluating it at. I figured out where they got negative 137 from.
Why?
So basically, like, the two things to connect here are basically the section where he first mentions negative 137 as the full tensor product over all three R's, and the second section where he actually calculates that negative 137 one value at a time. And you can see what he's doing is he's like, okay, so in this tensor product over the all three values, they're basically saying, okay, the value in the top left is going to be like 1 minus R1 times 1 minus R2 times 1 minus R3 times 1 minus R4. And value in the bottom right of this 4x4 grid is going to be like R1, R2, R3, R4. R1 times R2 times R3 times R4. And then the idea is that, like, the way you can calculate this sum of, like, you know, putting these numbers in this grid and like multiplying each number by like some either 1 or 1 minus R1, 1 minus R1 or R1 times 1 minus R2 or R2, one of these, is that you can break it up into the last two and the first two. And you do the last two on the rows and the first two on the columns. And then at the end, this computation gives you the same value, but you can split it in two. And lets you do like some interesting optimization stuff or ZK proof stuff, which is what like Binius is trying to do. Does that make sense?
Not really, but
Sorry. Let me try to draw it.
we're discussing tensor products.
Indeed.
You know that you're presenting, right?
I am. I can present. I read the post. It's kind of a neat place to use the whiteboard, I guess. I
Really?
guess you can walk on this.
I kind of like this. I think this is cool. It's very intimate. 9793. Also, it's streaming.
Oh, we have a webcam now?
Yeah.
Holy shit.
It's because we couldn't read the board previously, so I decided we were going to change that. This is
So this part I figured out.
stay
which
the
is-
same. Yes, this is everything. R1, R2.
The reason this works is because of like multilinear polynomials. Like this is how you write a multilinear polynomial from the evaluation points.
But independent of
into this.
multilinear polynomial, all he's doing is he's saying like, instead of multiplying each number 4 times and adding it up, we're gonna split this into 2 steps. First, we're gonna multiply all the numbers by the last 2 values, and then we're gonna multiply all the numbers by the first 2 values.
Right, but the reason this leads to a polynomial evaluation is because, like, this is how you convert a list of evaluations into a multilinear polynomial. Is by
I don't
doing
really
this.
know what those things mean in this context. Like, I don't know what multilinear polynomial evaluation, like, why does that matter here?
So this essentially he's taken, or not he, I think this is breakdown. Like I think what he's describing is breakdown. I'm not 100% sure, but he's taken a multilinear polynomial and he's converted it into a grid. And yeah, like
That's how you do the square and decomposition trick.
yeah. But yeah, the reason that this thing works is because like which it feels like he doesn't explain. I just had to fucking think until I got it, which I was really annoyed about. Is like why this even works in the first place. He's sort of just like, this is what we're gonna do, and it just works.
Sorry, it just works because. Sorry, like, you're saying this process of breaking the steps of multiplying by the last 2 values.
Okay,
like,
yeah, this
breaking
stuff
it
is
into
fine, but
protocol.
like, why does this lead to a polynomial evaluation? Tell me.
To be honest, it's unclear the polynomial we're even evaluating.
Well, the polynomial is this like 3141592 evaluated in this hypercube.
Yeah, where you multiply it by each of these values.
No. Like this is to get a polynomial evaluation.
Yeah, so at the end of this, you get the final evaluation.
Why? Why does that work?
Well, I don't even know what the original polynomial is.
It's literally this polynomial.
Because the matrices represent like all the coefficients of the polynomials.
Not coefficients, evaluations.
The matrix, sorry, this matrix 3141 is evaluations.
Yeah.
Yeah.
And the polynomial is this R1, R2, is on R1, R2, R3, R4.
Kind of.
And it's multilinear because R1, R2, R3, R4 are different variable names.
Kind of. Or like this, he's doing a specific, like, okay.
So I think when making this mark tree,
Yeah.
we got the one row as a one variable polynomial, because this block extends the polynomial. So I think.
Yeah, I didn't understand anything to do with the extension polynomial
Yeah,
either.
so this is the first polynomial with variable 1. This is the second polynomial with variable 2, and so on.
I don't think so. Like, it works here in this case because this is also confusing, I think.
Yeah.
Square root of 16 is also equal to log 2 of 16. So I think a bunch of things get muddied up here. But, like, basically.
Right, square root of 16 is log 2 of 16. That is very annoying.
So a bunch of things are really confusing. So basically, like, this, like, initial hypercube thing he has. This is so difficult to, like, parse.
3, 1, 4, 1, 5, 9, 2, 6, 2, 0,
I think this is actually the correct way to parse it is via an example, which is what he did, but I wish he had just given a little more explanation.
So I think roughly, like, this is the evaluation at 0, 0, 0 of the polynomial.
Yeah.
0, 0, 1. Oh wait, no, he uses the other thingy. Let's do this instead. Okay. 0, 1, 0, 0. 1, 1, 0, 0. And then you kind of repeat this. You do this for the rest of it, essentially. Like, this is a multilinear. So, does everyone get like multilinear polynomials? Like, does that thing make sense?
No.
Okay, so in this multilinear polynomial, there's 4 different variables: x1, x2, x3, x4, and you're evaluating them at different binary numbers, different bits, essentially. And the reason you do this bits is for the sum check protocol, which doesn't even get into in this post at all. But basically, if you have this multilinear polynomial, you're only evaluating in bits, then you have a nice like hypercube that's formed by like, yeah, basically toggling each of the 0, 1s at each of the different indices. So
No idea what you're saying. What indices, what's 0, 1, what's getting toggled? Like, this is the 0, 1. Oh, this is the 0, 1, right?
wait, what? Yeah, like you're evaluating like.
So, but you said this is evaluations, this matrix, 3, 1, 4, 1.
Yeah.
But it's not evaluation. This is coefficients of your multilinear polynomial, I thought. Like, this is your multilinear polynomial. You code 3 bits.
It's both. It's actually both. This is how you get from so this is what I was trying to explain before, is like how you get from evaluations to an actual polynomial is with the following formula.
Oh, this is one of those weird things where, like,
This is the Lagrange basis, where like everything except what you
Right.
want in this thing is
I
gonna be
see.
1.
Okay, so the evaluation of this polynomial at 1, 0, 0, 0, like the polynomial represented by like the bottom 2 rows here, everywhere, is 1, which is also the coefficient. Well, it's not really a coefficient of any polynomial. It's just the evaluation. It's like the coefficient of this like weird polynomial we've constructed out of 1 minus R1 and R1 and R2 and 1 minus R2 and all this other stuff.
One sec.
So it's not really a coefficient.
Spartan. Oh.
Ah, okay, I see. Ah, okay, I see. I see now why you keep saying the word evaluation. Alright, where are you at?
Real, isn't it?
Yeah.
Oh my god, hell yeah, that's
ChatGPT is
based.
the way to go. Sick.
Fuck, where can I find this? Spartan Streenox. Can you do me a favor? So YouTube is blocked. Oh wait, no.
You're literally a goon.
YouTube is blocked until 3:30 for Vivek. I'm sorry. Yeah, okay. Can you please do me a favor?
Yeah.
So
Sorry.
go to YouTube, yeah. And go to Srinath Study Spartan. you spelled Serena.
No, but
Yeah, it's fine. It's fine.
I don't get like the first word.
Srinath. Just like
It's,
Srinath. Oh, sorry, it's French. Oh, that's the French keyboard of the word. Oh, it's a little different.
Oh yeah, okay, it was a name, okay.
Okay, so let's wait for this ad to finish. Wait, why are we all like separate? What's the deal here?
I think they were going at a different pace. I don't know. I don't know why everyone's not here.
These are where the alphas be given out and my abilities.
Clearly.
I spelled it somewhere else, man. Oh, it's called multi-layer extension. Okay, nice. Now I can find it. Yes, the Taylor paper. Okay. Okay. Here's what is going on.
What is S? What is this?
S, I think, is a typo and supposed to be R.
Yeah, that was also annoying as fuck.
Yeah. Oh. Can we make like a PR to his blog and be
So I think the target of this proof system is constraints like air insert stacks. And this original polynomial can be represented by a single variable, but in general, if the variable x has a n bit, we can also represent this polynomial as a multi-variable polynomials with n variables, and each variable is just a binary. But when proving this polynomial, we can also put some random number for each variable. And the reason that we see this kind of 1 minus r is so first, this variable x1, x2, x3, x4 should be binary, so it just goes through all pattern of the all combination of these binary variables.
Okay, so basically, the way you get from a like monomial. Wait, no, not monomial. How do you say polynomial with just one variable? Univariate polynomial to a multilinear polynomial is through this equation basically, where if at a specific thing it evaluates, like at element e, it evaluates to like, sorry, e is 0 in this case, and in that case this polynomial z evaluates to 3, then you multiply it by this polynomial here, where essentially like you have the different variables that you're expanding to, x1 to x2 all the way to xm, you multiply them against like the bits of e in a way such that like this will only equal 1 if xi equals, or sorry, if x equals, oh yeah, if the bits formed by x1, x2, blah, 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 xm equals e, essentially. And so, like, as a result, when you evaluate, like, this thing at 0, 0, 0, 0, you'll get the original polynomial evaluated at 0. 1, 0, 0, 0, you'll get it evaluated at 1, etc., etc., etc. Does that make sense? I'm pretty sure this is key to, like, why this thing is useful in the first place, which is basically that, like, you're evaluating this polynomial at R1, R2, R3, R4. And that's, like, the same breakdown that this gives you when you, like, go across the matrix. Which is, like, never explained, so I'm guessing. But I'm pretty sure this is correct.
So I'm not responding because I'm gonna keep reading. Because I think he's gonna discuss some of this in the next section.
He doesn't.
Okay.
I'm sorry. You missed
Well,
the
I
alpha.
don't get is that he's saying that every row is like one polynomial evaluation.
Yeah, so that's what he does later, is basically he like reads Solomon extends each of these rows, and then opens up these columns,
Yeah.
and then you can basically do a thing where like read Solomon extension of a linear combination is equal to the linear combination of read Solomon extensions. But yeah, like that all only works because of like this setup, basically.
It's like when you say
Wait,
information
so
distance,
the
it's like
fir-
you
the-
go like 50% the speed because I'm still parsing.
That's fair. I'm just gonna get my iPad.
So I'm following you for the 0, 1, 2, 3,
Yep.
but then evaluate the same polynomial at 4, 5, 6, 7. So I don't get where you have like these evaluations though.
So that's like 5, 9, 2, 6. Like at 5, you're evaluating. Oh, sorry. The binary is like in reverse order,
Yeah.
where the most significant bit is at the
Yeah,
right,
yeah.
which is a notation he uses later. So I'm just sticking with that. And like
Oh, okay, I get it.
that's 4. That's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah.
Oh, there's another typo here where it's addition of multiplication tables, but it's another addition in the top left.
Which one?
Like where you have the tables. This should be a times.
Leave him be, man.
I know, but it just confused me. I was like, why are there two addition tables?
Are you meaning paper itself?
No, no, no.
Ah.
This is just still a blog post.
I feel like the paper itself is, once we're done with this post, we can get to that.
I was reading the paper last night. It's very nuts, yeah. But yeah, a lot of the words make like about 4x more sense after going through the blog post.
Yeah.
They were just like saying things the first time I tried to get through this. Cool, man. That's awesome. I'm happy for you. Oh, okay, they also do the extension thing here. Yeah, okay. Nice. What are you reading this like from?
Well, look at my laptop screen.
Oh, damn.
I really should have done the other way around,
Hero.
but it's fine. I'm okay reading it on my phone. I can also annotate then. So x0 is like 1 plus root 5 over 2, but that doesn't really matter because you never really think of it that way.
What's x0?
Like the first extension of the binary field. First extension of it.
You solved the quadratic equation.
I was like, yeah.
Nice. No, I don't
Like,
think
does
so.
it have an I in it? It doesn't.
No, it's just like, it just extends the field. It's irreducible. That's why they renamed their whole ass company after this shit.
What does Olvatana mean?
It's like some mountain in fucking Antarctica or something. There's like the dumbest shit ever.
Don't say that on stream.
Oh, shit. Well,
Well, I mean, they changed it, so they probably would agree. It's also impossible to spell.
yeah.
That didn't help.
So let me clarify my statement for any people watching this. It's a cool thing, but no one knows what it is. And once you do know what it is, it's like cool. But
Well, how is it related?
irreducible is a much better name. Sorry. To the one viewer that will ever see this stream.
I was considering putting it on Twitter, like learn Binius with us.
I feel like this is not helpful. Like, if anything, we should give a stream about like us actually understanding it and teaching it.
Do you think it's cool to see cryptographers in their natural habitat?
Like, it's not that interesting.
Okay.
We're just like sitting here reading for like 80% of the stream.
Yeah, but like I think it's like cool
Well,
to convey to a
if
person
Vivek
that's what it is.
ends up giving a presentation, then we can say that. That makes
Yeah,
sense.
that I'm happy to stream and like record and do well.
I guess to me it just seems like these things never happen, so this 80-20 is the only way we're gonna get stuff like this out.
I see. Okay, so you extend that. So
I am so confused. Why would you ever want to accept, like, represent a number in terms of x0, x1, x2, x3?
because then you can do, it's a binary, it becomes a binary field.
x0, x1, x2, x3, these are super random values.
Yeah, you never like use those values. These are just like variables.
You ever use the property x squared equals x plus 1?
You do, you use that property.
I see.
Yeah. But you never think of it as like 1 minus square root of 5 over 2 or something like this.
Right, okay. But it lets you make sure that nothing ever exceeds degree 1, I guess, which is kind of nice. Because it ever goes degree 2, you just place it back to degree 1.
Yeah,
Cool.
precisely.
But it probably wouldn't matter if it was like x0 plus 1 or x0 minus 1, it's just kind of irrelevant.
x0 plus 1.
Like, it's irrelevant as x0 plus 1.
It just needs to be irreducible. I actually don't have a good sense of what makes something irreducible. I mean, I guess it's just that its roots are not in F2. So you can't reduce it to within F2, basically.
Roots are not in f2. Sorry, what's f2? Oh, like it's not 0 or 1.
Yeah.
Okay, well, we knew that much.
I mean, I guess that's all it is. Because you don't have any other numbers to be able to like reduce it into.
Not in f2, why don't you just say it's not 0 or 1?
Because it's irreducible over F2.
I see.
But yes, you're right. That is a pretentious way of saying it's not 0 or 1. I also finally understood what fields of characteristic 2 meant last night. That made me really happy.
Is that just this?
It's binary fields, and it's fields where if you take the additive identity,
Yeah.
1, it's how many times you need to add it to itself to get back to 0.
It's just mod 2.
In the case of binary fields, adding 1 to itself is always going to be 0.
Yeah.
So all binary fields are fields of characteristic 2. And people love saying this shit in a bunch of places where they talk about
Yeah.
Binius. It's like, oh yeah, it's just fields of characteristic 2. It's like, what the fuck is that talking about? And it's just another pretentious way of saying, yeah, like 1 plus 1 equals 0. That's all that was.
Isn't that just like zoning?
Huh? Exactly. No, exactly. Like it's Zoring 2 elements together will lead all zeros. Yeah.
So I have this like one doubt, like why have they shown this particular statement using this last column? Like how does that work?
Okay, so you take the rows, right, and you read Solomon extend them as if they were all polynomials.
Yeah, so like they did it here.
Yeah. So
So this like array we got via the tensor multiplication, tensor product
of the
of
rows.
3 and 4. So
Yeah.
like, so initially this said that okay, this is like one particular element in the hypercube, 1, 2, 3, 4.
Yeah.
And then they said to break it into 2 parts, like 1, 2, and 3, 4.
Yeah.
So getting the tensor product of 3, 4 gives us this array of numbers, which is like 6, minus 9, minus 12.
Yeah.
So they're basically applying this computation on initially the initial hypercube flattened.
Yeah.
But like, why are they showing this as equal by using this particular column?
So yeah, basically like the interesting thing here is like you can if you do it's basically like this operation works like in either direction, and it's a way of verifying that you've done different steps correctly. So in this case what you've done is you've multiplied it against this tensor product of the things
Yeah.
before, and it yielded these 4 numbers.
Yeah.
And then if you read Solomon extend this, which basically means you evaluate the polynomial at more points defined by these 4 things,
Yeah.
then you get to this.
I get that, like, but when we are saying like we calculated the tensor product of 3, 4.
Yeah.
What does that mean?
Oh, that's basically like the 6 minus 9 minus 8, 12.
Yeah, but like that's the output, but like
Why?
What is like that in the initial flattened hypercube? What is
What?
like 3, 4 in the initial flattened hypercube?
So that's basically like you're evaluating this polynomial. So this polynomial was originally defined over 4 variables, right?
Yeah, so like
1, 2, 3, 4.
okay, so like out of the 16 elements, like which is 1, 2, 3, 4?
It's not in these 16 elements.
It's like extrapolated or what?
Yeah, exactly. It's extrapolated. Like you define a polynomial based on these 16 evaluations, and that uniquely defines a multilinear polynomial with, I don't know what degree it is here. I guess like, I don't know.
So basically, we want to calculate 1, 3, 2, 3, 4.
Yeah.
And they are doing it by breaking it into 2 parts.
Yeah.
And then 3 and 4's tensor product is calculated.
Yeah.
And they want to show the property that linear combination of Reed-Solomon extension is equal to Reed-Solomon extension plus the and after you do the linear combination.
Yep.
But initially, so what they're trying to do is like they took 3, 4's tensor product.
Yeah.
And they multiplied it to get an array.
Yeah.
And then they did the Reed-Solomon extension, and then they multiplied it, and then they got another array. But like, why did they choose the last column to show that this thing is equal? Like, how is this 6 minus 9, 8 corresponding to this last column?
So basically, all he's trying to show here is like you can query any of these columns, and actually in the actual protocol you query multiple to get like more certainty. Any of the columns, if you multiply them by the tensor product of the 3 and 4, is going to yield an evaluation that's part of this Reed-Solomon codes extension. Like you can do the math for these guys, and it should equal -849.
So basically, he's just saying that like that last column is just an example. You do it on any column, and you get the same. answer.
And you will. You do it on like many
Yeah, yeah.
columns.
Oh.
Yeah, exactly. That's good. Wait, can we keep going through this row thing? Are you just like writing out these things?
My vibe. People get the idea right. I wrote them out. We just write one of them out in the middle or something. Unless you want to write them all out. If you want to write them all out, knock yourself out.
Wait, it just doesn't click for me. Like, oh, okay. It's everything on the top is 1 minus R3, 1 minus R4,
Yeah.
and then it goes, just cycles through it. Okay. Yeah, I'm good.
Sorry, may I ask a question?
Yes.
So the purpose of so I'm reading this simple Binius section,
Yeah.
and the purpose here is the program want to show the result of this merge variable polynomial z at some specific evaluation point.
random
point.
evaluation
Yeah.
point.
I think it's actually this x should be okay. Anyway, if you want to prove prove the result of this, and this should be equal to this equation, because if each x and xi and er is just a bit,
Yep.
it is this part will be one.
Yep.
If and only if x is equal to e.
Yes, exactly.
Yeah. So actually, only the time first equation part is one remains here. So this will be equal to zx.
Exactly.
This part, and we compute this kind of tensor product because when we ignore this xi and just consider ei plus 1 minus ei, and multiplying.
Well, like
this
one of those is going to be 0, right?
Yeah, and the time of this product, each time of this tensor product, just product, is corresponding to the tensor product of this 1 minus r and r.
Yep.
And instead of computing this equation directly, we separate this one as a kind of square form.
Yes.
So we can reduce the computation cost to n to the root of n.
Yes.
Okay. And my
Exactly.
question is, but I think in this simple Binius,
Yeah.
it does not consider this xi or mn, and it uses random r instead of bit here. So I think this is not, this description does not follow this idea.
Well, so basically, like, what's going on here is you have 16 evaluations of this polynomial,
Yeah, yeah.
right, across this Boolean hypercube. So you can use this formula, which is called the multilinear extension, to define the unique polynomial with, like, I don't know what the degree equivalent is in multilinear polynomials, but it's sort of like, at most you have 4 variables,
Yeah.
and at most, like, 4 of them are multiplied together. So it's like
Yeah.
degree 4, like, you define
Yeah.
a unique degree 4 polynomial over these 16
So
evaluations.
you mean low degree testing, right?
Huh?
You mean low degree testing?
No, not low degree testing. Like, this is literally just like defining a unique polynomial from these evaluation points.
I see.
And like,
and-
so you use these 16 points to create this polynomial,
Yeah.
and then you have the polynomial. And then after that, you can query it on different points that are outside the Boolean hypercube,
Yeah.
and you will still get like correct evaluations, if that makes sense.
I see. And if we evaluate random out, so if we put the random out to xi or er, of course this result will not be equal to the original this x.
Yes.
But it's okay because as long as it's evaluation, so it's okay as long as linear combination of the extended extension value
Yep.
is equal to the extension field of linear combination, as this Peter is brought.
Extension field? What do you mean extension fields?
Extensions
Reed-Solomon extension?
as it's a extended field of the how can I say? So I think it
Well, it's just like
extends the
Extends the polynomials like
extends
domain or something.
yeah
or
domain yeah yes.
range.
Yeah
Domain
extends
is
the domain
fine.
years.
Yep.
Okay, I understand. So I think this technique says is given yeah, but I still don't understand their complete. So I think I should read the foreign part now.
This part isn't relevant to this. Like the simple
Okay.
Binius doesn't use any binary fields. I think this is just breakdown.
Okay,
I'm
okay.
like 70% sure.
Okay.
But I'm not 100% sure. Okay, so then I also gonna want to mess around with this tower a bit more. I feel like I don't have good intuition for why this works. There's also a really good talk from Ben Diamond on the tower where he explains in a bit more detail. And he also goes through like how to do multiplication and addition. I think it's the PSC Learn and Share, or maybe a different talk, but I forget the details. That was like a few months ago. Binius, I don't give a fuck.
Okay, okay.
I'm joking, I'm joking. Okay, this fucking full Binius though is an absolute mindfuck. Oh lord. Yeah, I feel like there's so many things he skips in this. But now this like tensor product thing makes sense, right?
Yeah. So tensor product represents each. So tensor product represents each term of this part.
Exactly.
Yeah, and this each part here also represents this ZK.
Exactly.
Yeah.
Yep.
Okay, thank you.
Nice. Okay, bet. So it makes sense why simple Binius works. I think I understand simple Binius intent. I guess like wait, one thing. Wait. Okay, so the verifier can also generate these tensor products themselves, right?
Yes.
So then, and does the verifier doesn't have these evaluations, right? Like this is
yes.
your witness basically.
Yes.
I see. So you have to trust. Okay, so the prover gives them this essentially.
Yes. Prover gives this one and this one.
Right, and then the verifier can open up these guys and it can compute these same row combinations
Yeah.
and get this.
Yes.
And then it's like, cool, I know this is all the same or like I have good faith that this is kind of all the same polynomial basically, or that you've extended all these rows correctly. And then once you want to get the actual evaluation, you just evaluate this times the column tensor product. Nice. Okay. Cool. Yep. That makes sense. Great.
Or just their floating.
Also, like, is Binius limited to like hypercube, or like hypercube is just used as an example? For
Yes, it's limited to multilinear polynomials.
Yeah, but like till fourth degree, or like you can expand it to like.
You can do as many degrees. Like the degree or like the number of variables you choose in your multilinear polynomial is just however many you need to like represent your entire computation trace basically. It's just like with Planck, you know how you do like 2 to the k variables, or like Grot 16, you have like 2 to the k different variables in your polynomial. It's the same thing. It's just instead of in one row, it's in a hypercube. He also never explains why that's useful, which is basically just for sum check. You need to do sum check, you need to be able to have a multilinear polynomial that's evaluated on like Boolean values like 0 and 1. And the nice thing about sum check is that you get to avoid multiplication, you get to avoid FFTs and this sort of thing. But yeah. I think if you want better intuition for multilinear polynomials, it's worth learning Spartan, because Spartan is like the simplest multilinear snark. It's like the first one. Srinath was a fucking goat for inventing it. And yeah, that explains it really well. And then Hyperplonk takes it to the next level, and then this shit goes like fucking 16 more levels deep with it, so. Oh yeah, if people want to figure out the carrot suba thing, that sounds fun.
I literally just got to that line.
Nice. I think that's something that seems doable. post gives like absolutely zero intuition for performance.
Correct.
Unfortunately, this is just like fun math for the gang,
That's true.
which is great.
Yeah. Not too bad. Like an hour and a half session, do some fun math, go back to work. Pretty good. This 42 example he gave, like, doesn't say over what binary field it is.
256. You can guess by looking at the numbers and the fact that 42
You
and
can
255.
guess, but like, wait, he's not explaining like which extension field it is.
What do you mean extension?
Like his whole shtick is like, oh, we do this weird notation and there's like x0, x1, x2, x3. Like, shouldn't there be some number of x0s, x1s, and x2s and x3s here? And this is his like weird left first representation.
I mean, I guess he's just saying like he's just basically saying it's like modular arithmetic. Like, this is basically just mod 256. I think.
Is that really true? That x0, x1, x0, x1 thing is just modular arithmetic, is that they operate the same?
No, it's not. Wait, let me think. Oh, okay. He's just saying like modular arithmetic, it'll always stay within the same bound.
Yeah.
Yeah, basically, yeah, this is the like 7th tower, or 8th tower, I guess. And yeah, these are all being implicitly represented as the weird polynomial thingies,
Right.
but he's just not showing you any of them. Yeah, this might be more confusing than helpful, to be honest.
Yeah, I feel like that was.
Like people spending an hour and a half grokking this post and then getting a nice walkthrough will be very productive, actually. Because at least like there's be a bunch of bits, and these bits can become words.
Are you giving the nice walkthrough, or are we just going through his picture and being like, this the walkthrough?
I mean, I can give a nice walkthrough once I like get the last part. I can give a nice walkthrough the first 2 parts though.
What did he use to make these diagrams?
Microsoft Paint.
No way.
I'm not sure. I like non-trivially think it's Microsoft Paint.
There's no way.
I just what it's not fucking Excalibur. It's definitely not Figma. I think he's a Microsoft Paint legend. I also just like that idea personally, that like he's still using like some dinky old MS Paint software to make all these masterpieces. The artist is not limited by his tools. What are you working on right now, Sora?
So I'm raising how each bit corresponding to the variable.
Nice. Oh. Yeah, I need some fucking help with full Binius.
same example here as he used in the rest of the post.
Well, he can't because it's a different setup. Like the evaluations at each of the points are binary now.
Right.
We're in F2 now, baby.
Right.
But how did he get 11, 4, 6, and 1? Mod 16? No.
It's not 24, which is kind of random.
No, it's binary field stuff. Oh boy. Alright, so I'm gonna do some binary field math. Okay. 15 plus 8. What are we doing? Oh, it's just XORs. We're fine, we're chilling. So 1, 1, 1, 1. With 0, 0, 1, 0. Then 0, 1, and then 0. XOR.
Oh, like you expand each number out and then you XOR it. Oh, sheesh. Okay, got it.
I got you doing math. It is indeed 11. Wait. No, I got 13. What the fuck?
Move somewhere. You did it backward, maybe?
Oh, I have to also do 0, 0, 0, 0. Shit.
Why?
Oh, that doesn't change anything.
No, no, you did it backward. You're reading it backward. The bits are flipped, remember? Like 1, 1, 0, 1 is 11. Not 13.
Wait, what are you talking about? Like, that's just the entries in the field.
His notation is leftwise first, so what you're reading as 13 is actually 11.
No. It's like, no, I reversed it the right way. Like, I reversed it his direction, but these things are not numbers. 0, 0, 1, 1. Those are all evaluations. Like, that's not in binary notation. It's just like the row evaluations that you multiply by 10.
So 10's not like a binary number. Yeah, I'm super confused. I don't understand how you got 11.
Cool. Oh, I just missed one. I'm an idiot.
Ah.
So XOR with 0, then it's 1, 0, 1. That makes sense.
You got 11?
No. Just that XORing against 0 gives you the same thing. 1, 0, 0, 1. What the fuck? See, order operations matter here. Go. 15 is 1, 1, 1, 1, right?
15 is 1, 1, 1, 1.
Yeah. Oh my god, monkey. Okay, just keep fucking this shit up. So this is. Okay. We got to 11. God is good. Figured it out. It's just binary field addition on the columns to get to 11. And I just thought 8 was 0, 0, 1, 0, but it's in fact 0, 0, 0, 1.
Yeah, can't help it there.
Indeed. 0, 0, 1.
Maybe can explain how they are
Sora has it.
Yeah,
Or
it should
the-
be well, I'm not sure.
So one bit, first bit means 1, second bit means x 0.
Oh, okay.
I can share the profile.
Yeah, just write up the
Okay,
thing.
so it's a bit it's a white. Okay.
You always check now.
I have mistake before. So when in the Binius block, when converting the binary feed representation into the variables, it's how it corresponds. So how? So first bit is second bit is x 0.
Sorry, you can use another marker.
Okay. This one is also bright one. White one.
Wait, this one?
Yeah.
Maybe?
Thank you.
I don't know if it'll be any better, to be honest. We need this one. This shit was goated.
Okay.
Yeah, I think that is good enough.
A little bit light. Doesn't show up that well.
Yeah, I think this might be doomed.
Well, I think if you use the dark red marker, it'll be fine.
I don't know where that went.
It's not one of those?
No.
Oh.
Is it over there?
This one?
No.
Well, I mean, this black one would work too now.
It's a whiteboard marker. It is.
I mean,
It's
it's
a
not.
or-
Just leave it.
or-
There are books full of them, like just right here.
Oh, sure.
The box. Oh, here.
Oh, nice. This is the goated marker.
I can't really
So-
read this scripts, but
So that like the thing you have written circles are the bits.
Yeah, so it means first bit
I
means
see.
1, second bit means x 0, third bit means x1, and so.
How are you extending that?
So the Binius block have a example in the so I think it has a example. So basically I checks that equation, and when although some parts are missed, I think its order is like from multiplication of small number times large number, and large number large index variable times small index variable. So maybe some term might be wrong.
So you're
Right.
saying like because x1 and x0 x1 are 0, it is not visible in the final result.
Yes, but following the rule of this order of this representation, I think this word is correct.
And like yeah, I understood that, but how do you decompose it like from starting like?
So
Wait,
for
I think-
example, it has the whole of the bit
You're doing it?
Yeah, no, like this is one way of thinking about it, where like you basically break down everything into separate variables.
Yeah.
Like I think a slightly easier way that also comes into play, like at least he claims it comes into play later, is like take your number, split it into 2 halves, right? So because this has 8 bits in it, this part, like this top part, you multiply by x3, like if something is like
log 2.
huh?
Log 2 of the number.
Log 2 of the number of bits.
Okay.
So okay, now you have this. So you break this down, and then break into 2 halves here. So you have 1 1 0 0 plus what is this going to be?
Log x2.
Yeah, exactly. So it's 1 0 1 x2. So you have that thing, and then on this side, what are you gonna have?
Log x3.
You already have this x3, but like, how do you decompose this thing more?
So like again 1000 plus 11 111.
Yep.
You would add x2 at the end of that as well.
Or x3.
Got it. Okay.
Okay, so then you keep doing that. You just keep breaking this stuff down. So this guy, what does this become?
1 1 and 0 0 x1.
Which is just 0.
0.
Okay, so next, this guy.
1 0 and 1 0 x1.
Yep. Times x2. Okay. Plus, okay, this guy.
1 0 and that rest would be 0.
Yep. And then this guy.
1 0 and 1 1 x1. I think you missed 1 1.
Yeah. Wait, what did I miss?
No, okay. I was reading it wrong.
So I'm gonna make more space so we can fit everything into one line. So 1 1 plus 1 0 plus 1 0
x1.
x2
1 0
Yep.
plus 1 1 plus 1 1 x1.
And then we can finish this off.
It would be 1 x naught.
This guy?
Yeah, x naught. Like 1 into x naught would be x naught.
Right, so what does this become? Sorry, I kinda gave it away.
1 plus x naught.
Okay, perfect, yeah.
Yeah.
And then
1.
1
And then x1. So 1 plus x1. Then that would be 1 plus, it would be x plus x naught x2 plus,
wait, so what's this?
so let's keep it in brackets. So that would be 1 plus x naught. That would be 1 plus x naught times x1 times x2 times x3.
Oh boy, here we go. Okay. Times x2. X3. Okay.
Yeah.
So now it's just algebra.
Yeah, we open it.
We just finish this off.
x2 x3
x2 x3
x naught x2 x3 x1 x2 x3. I think we're done.
One more term.
X naught x1 x2 x3.
Yeah.
I see.
And the terms which are 0, so like x1 x naught x1, those are like zeros. So like x1 is 0.
Exactly.
Cool. So does that mean like in this entire thing, like wherever x1 is coming, that term is 0?
What do you mean? Wait, sorry.
So like, okay, so when I'm writing x1 x2 x3, this is like the product according to the binary arithmetic, right?
Yep.
So here can I take it into assumption that x1 is 0? Because the third bit is 0, which corresponds to x1, so x1 should be 0.
X1 is not 0. Wait, what?
Okay, so because in the original number,
Yeah.
the third bit is 0.
Yes.
And based on like what Sora has written, the third
Yes.
bit corresponds to x1.
Yes.
So does that mean x1 is 0?
Yeah, there's no x1 term in this equation.
No, there are.
No, but there's no solo x1 term.
But when I'm saying x1, x2, x3
Yeah.
in binary arithmetic, like
Yeah.
how it is defined, like can I take into consideration that x1 is 0?
Let's see, is that how this is working?
Like would x1, x2, x3 be 0 times x2 into x3?
0 times x2 to x3. Wouldn't that be 0? Would this term become 0 then? I'm like lost.
But then can't we, like, then x1 does not equal to 0.
So there's like an x1 term. I think, wait, is this correct? This listing here. Wait, so.
I created it in like a brute force way.
Yeah.
So I'm not sure this is actually correct.
But I think
But,
that is
yeah.
correct. I mean, the 1-to-1 mapping does seem to work out.
Well, I think.
I think if we do that in the same way with the all 1-bit string, we can check.
But that's not what this corresponds to, right? Like x1 here, x0 is 0, 1. This is 0, 0, 0.
No, I think
One.
there is some mistake in the above one because I don't think so. We have x0 and x3 as the term, but the 13-bit is 1.
Right. Yeah, I don't think this is
We don't have that term.
correct. Oh, it's the 9th bit is x3. Oh, these
yeah,
are the
yeah, yeah.
bits. Okay. No. Yeah, I think this is correct still. So this just basically means if you have that term, you have a 1 toggle at that bit. So for x2, we have a 1 there. x2, we have 1 toggled at the 5th bit.
This is, I think it's x23.
Oh,
X23. Yeah, that's what I'm thinking. X23
We still don't have
is
x2. Oh, we have.
correct.
Okay. Yeah. Then it works out.
Nice. Okay, yeah. So this just means what bit is toggled
Yeah.
in this whole equation.
Yeah, but when I say the third bit is not toggled, does that mean like x1 is 0 then?
Yeah, like we have implicitly we have like a plus 0 times x1 term
Okay.
in this.
Yeah. So that doesn't mean x1 is 0. It just means the coefficient of x1 is 0.
Exactly. Yes. Yeah. So these are both equivalent ways of thinking about it, like toggling bits or breaking it into halves, basically. Did that register for other people? Take that as a no. Also, this is a wild one to be your first dive into ZK stuff.
Yeah.
Yeah, no, this is. Yeah, don't even worry if this stuff doesn't make sense. This is basically his most complicated ZK Snark blog post by like a mile. Stark Part 3 is pretty good. That's a personal favorite. Plonk is good.
I feel like at the end of this, I have like a little bit of understanding of each individual component, but still, if you ask me to explain full Binius,
Yeah.
no chance.
I don't know the flow, like how is it working? I know parts of it, like I understand that. Like
I think I'm getting pretty close to the full flow. At least like that he's described so far. There's like another 6 parts he does not describe, so we're very far from actual Binius.